Okay, 3.3, separation of variables. In this section, we shall attack Laplace's equation directly using the method of separation of variables. So Laplace's equation, del squared v equals 0. That's what we want to solve. Rather than coming up with these little tricks and doing these method of images and other things, what if we are to solve it directly? Okay, so here's an example. You've got two grounded planes, and then along this wall you've got some potential, and the question is, how does the potential change as you go from x equals 0 to x out here? Okay, so we want to find the potential as a function of x in this slot. So we have to solve, since it's independent of z, since their symmetry is on the along the z-axis, so that as you move this way, the potentials are grounded across z, and v is grounded across z. So there's, whatever it is, it's symmetric along there. So what we need to solve is Laplace's equations, and we need to make sure it is subject to the following boundary conditions. That v equals 0 when y equals 0, because that refers to this grounded plane, and then v equals 0 when y equals a, at that height a up there. And then we also, because it's 0 up there, and then we also need to make sure that v is v0 when z equals 0, and when x equals 0, not when z equals 0, sorry, when x equals 0, because all along x equals 0 along that plane, v equals v0. And then we need to make sure v goes to 0 as x goes out to infinity, because as we go further this way, we get further and further away from v0, so we need to make sure it goes to infinity. Okay, so then what we do, in order to solve this, we need to look for a function that, if we take the two derivatives of it, second derivative with respect to x and with respect to y, that it's equal to 0, that basically this is equal to that. The derivative with respect to x is equal to the derivative with respect to y. That's what this equation is telling you. The rate of change of x is equal to the rate of change of y, and you need that to be the case because you can't have any minima or maxima, so they should change together and be equal and opposite. So if it goes down in x, it better go down in y, and so on. Okay, so the first thing we do then is to look for something that is something x times something y. Okay, so that's what this is saying. We just need a solution that is two functions, something that's a function of x times a function of y. So we can't have a function that's 4x plus 2y. Okay, that's not x times y. We could have 4x times 2y or 8xy. Now that is something we want to look for, something that's x times y. Okay, so if you plug this into that, for v, then you get the second derivative of x times y with respect to x squared, plus the second derivative of x times y with respect to y squared. And then you get this thing, because the y is not a function of x, and then the x is not a function of y, so then those derivatives of those from the x component doesn't do anything. And then what you do is you divide by y, divide by x, to get the x things together and the y things together, and then you look for a solution like this and like that, and then you know that this and that have to be the same, they have to be equal and opposite to each other. So you say that, okay, this has to be a constant, that has to be a constant, and they have to be equal and opposite. So then the second derivative with respect to x has to equal x times some constant squared, and then the second derivative with respect to y has to equal minus y times some constant squared. Turns out that the solutions to these are exponentials and sines, okay, because you need two derivatives to give you the same function after two derivatives. If you take sine, you get cosine for the derivative, and it gets you back to sine with the second derivative. So that's a nice one. The exponentials derivative of the exponential gives you the exponential back again. Derivative of e to the x is e to the x, so no matter how many derivatives you do, you get the same thing. But this minus sign on there is why we use the sines and cosines, because if you take the derivative of the sine, you get minus cosine. If derivative of cosine, you get sine. So you're left with a minus sign after two derivatives. How cool is that? So then our x thing has to be something like this, and our y thing has to be something like that, and our overall solution has to be the x thing times the y thing. Okay, and that's what we're looking for, is a solution like that. So this is in general where you get every time. You get something like this every time, and now we need to apply the boundary conditions for our problem. So in this case, we're left with this function v of xy, and that's equal to this e to the minus kx times this. Why? Because in order to meet our boundary conditions, a e to the kx goes forever, but we need it to go as x goes to infinity. So as x goes to infinity, this number blows up, so we need to make our constant a 0 to kill that thing off, because there's no other way to get that to be 0. So then we're left with just that part of the formula, and then what you can do is you can take b and just factor it into c and d, and then just have e to the minus kx. So that is where we get to here, okay? And then what we need to do is apply another boundary condition, and for condition 1, we need at y equals 0, at the grounded conducting plane, y equals 0, v has to be 0. So cosine of 0 is 1, so d has to be 0, so that at y equals 0, we get 0, so we kill that because at y equals 0, sine of 0 is 0, so that's nice. So now we have this thing here, v of xy is equal to c is equal to e to the minus, did I just go, I don't know why I did that. Okay, anyway, so now we're here. Now we've got another issue, because our other boundary condition, we need y equals a to be 0, okay? So we need y at a to also give you 0, because v at x and a, where y is the height of the second plane up here at point A, that has to, v better be 0 at that point. So for that to be the case, for this to be equal to 0, if we make, since x isn't affected there, if we make y equals to a, then we get sine of ka, but we need to make sure that's equal to 0. That's only 0 if k times a is 0 or pi or something, because sine of pi is 0. So we need this to be some integer of pi. It could be any pi. It could be 1 pi, it could be 2 pi, it could be 3 pi. So as long as k is some n pi over a, then that times a gives you n pi, okay? And so k has to be n pi over a, and it can be any n. Okay, this is a problem, because that means that we can't really specify what k is, because we have an infinite number of solutions. Which one is it? Well, it turns out that going through here, and I'll just let you read all this because it's a lot to go over, but the solution here is that it turns out that it's not just one value of k, it's actually all values of k for every n. And so what we need to do is actually add up all of the k's. We have to do an integral. We have to do a sum here we need every one of these combinations to come up here. So that means we have these boundary conditions such that we need our solution, our y value at y equals a, we need to add up every possible c value to give us the solution. So that's what he does here, is he says, okay, well, we can draw any harmonic function as any combination of sines and cosines. So that means we're going to have some sort of oscillatory function in here, right, and it's going to decrease as we go down here. And so we need to determine what that looks like. And so if we have some weird, harmonic function that looks like this, but it would be better if I actually made it look like it was repeating. So if okay, now if we imagine and then it would repeat outside of this thing, we can write as some combination of just regular sine waves. If we add them all together, then we get this kind of weird shape. So that's what we need to do, is we're going to say, oh, it's a combination of all of the different things. So let's just go ahead and integrate all of them up. Let's add them all together. So then what we are going to do is we say that we're going to integrate everything, both sides of our function. We need this to equal our boundary condition. We're going to multiply both sides by some m prime value to pick out a given n, let's say. And then it turns out that it's only true for a specific n. And then we integrate for that n from 0 to a, and then we see, oh, if n is equal to n prime is equal to n, we get a over 2 and then that turns out to be our coefficient. So then c sub n is 2 over a times the integral from 0 to a, and then we get that c sub n is this integral, and then it turns out that if n is even, you get 0 because sine, well, you get cosine there. But if n is odd, then you get 4v0 over n pi. Then you get this mess, okay, and there's our potential. It's 4v naught over pi times the infinite sum of odd ends, and you keep adding them up, you get closer and closer and closer to the true potential, okay? Hilarious, right? So there's the true potential, okay, after 100 n terms, there's your n equals 1 added to that, n equals 2, add n equals 3, sorry, n equals 1, n equals 3, n equals 5, n equals 7, up to n equals 100, and the more you do that, the closer you get to the true potential, and there's a long one, and then there's along the next, and there's and you add them all up, and then okay, and this is how you can solve for the potential in this region, okay? And then it turns out that this series, this sum here, actually has a solution, that you can you know, turn it into a regular function, and that's what it is, the inverse tangent of sine over sinh. Okay, and that, if you want to prove it, Laplace's equation, that del squared v equals 0, and you can, in the region between where there's no charge, you can solve that and prove that that's the case. Okay, so that's kind of amazing that you can figure out just from the boundary conditions what your function is, and then you got to do this Fourier trick. I expect you to be able to do that. I expect you to read this thing and figure out what's going on here, and be able to do that. And if you have questions about that, come find me. Otherwise, forever hold your peace. Okay, and then we got another example here, 3.24. Instead of one end being open forever, it's boxed off, and just a different set of boundary conditions. So you're going to have a different, again, you get to this point, and you start to apply your boundary conditions, and then you do your Fourier's trick again, and blah, blah, blah. So make sure, and there's your potential, whoop, goes back up to the other side. So make sure you're doing that, and you figure out how to do these so that you have an understanding of that problem. And then there it is in 3 dimensions. I am not going to expect you to do a 3-dimensional problem on the exam. I will expect you to be able to do the other 2 problems I just talked about, and but this here is a little just too much time to be able to do. But you should know how to do that, so you may as well read through that. Okay, and then in spherical coordinates, again, instead of x squared, y squared, z squared, depending on the geometry of the problem, you might want to look for that. And again, you just look for, instead of functions that are x times y, you look for functions that are r times theta. And then the solutions you get are called the Legendre polynomials, okay? And the functions of theta are these PL cosine of theta, and you know, P0 is 1, P1 is x, P2 is 3x squared minus 1, and so on. And these are the Legendre polynomials that are the solutions to these types of things. So the general solution is a linear combination of these a sub L, R to L, all these things, times your PL of cosine theta. And so it's either 1 cosine theta, 3 cosine squared minus 1, 3 cosine cubed minus 3 cosine theta, because we have P 0 of cosine theta when we do these problems, okay, in general. Okay, so when it says PL of cosine theta, you replace x with cosine theta to get your Lth thing. And so this would, you know, if you added a few of these together, you'd have A0, R0 plus B0 over R to the 1 times P0 of cosine theta is just 1. So that's your first value, okay? And those are, again, your coefficients A and B that you use to satisfy your boundary conditions. Okay, so for example, let's say you've got a potential on the surface of a sphere that's hollow with a radius r. What's the potential inside of the sphere? Okay, B sub L equals 0 for all L, otherwise the potential will blow up at the origin. So if you look at this thing, your potential needs to be 0 at the origin. Well, it can't be infinity. So if you put r equals 0, then this goes to infinity, and that's bad. So b needs to be 0 in this case, because at r equals 0, you don't want infinity. So that leaves us just with this. And then you do the same thing at r equals r. We need to have v. So then you have your sum of everything, at r equals capital R has to equal v0, so you set them equal to each other. Okay, and then we do our Fourier trick again, and we integrate from -1 to 1 on one side, and then 0 to pi on the other side to match the two together, and then you have your 0 for L prime equals L, and then 2 over 2L plus 1 for this one, and then blah, blah, blah. You do the same sort of trick, and then you get your potential and your boundary conditions and the terms of the Legendre polynomials, and then you replace what P0 of cosine theta is with P1 of cosine theta, and you get 1 for P0 cosine theta, and then you get cosine theta for P sub 1, and then that's your potential, okay? And that's it. That's the whole thing. So pretty cool, pretty awesome, yada, yada, yada. A couple other examples here to do that you can just kind of play around with. I'm not going to give you a problem that's the spherical problems, but these are good to study. The problems I will give you are the first couple where we have Cartesian coordinates, just because they're faster and easier to do. Okay, bye.